Hey guys, sorry it's been so late, and I have some bad news. I was going to continue reacting to this audiobook, Astrophysics for people in a hurry, but I could not find the place to start it. So I've made the executive decision to restart it and actually take notes from this point onwards as to like when we finish the part one and like the timestamp of this audiobook because Audible is not saving it for me for some reason. So we're gonna start this again from the get go. Um, Let me just put a little thing here that let's do that. That should just be good enough. And then if we pin that, that should get us going. Alright. So we're probably going to do maybe about an hour of this. And the funny thing is I can't even really remember part one. So, like, what I already did previously. So, we're just gonna start it and enjoy it, hopefully. Hopefully you guys enjoy it too. There will be pauses for me to talk and react to because in order to react to something, I have to put my own 2 cents in. So, sorry about that if it annoys you. Let me just check my stream real quick to make sure it's actually up and running. I think it is. We pauses for me to. Yep. Alright, cool. So we're good to go. We're just gonna chill, listen. I'll be pausing and talking about what I hear and my responses and stuff like that. And we'll probably go for like an hour or something. And we'll see where we are at that point. Alright, let's start it.
This book is read by
what is that?
Neil deGrasse Tyson.
Why is he saying that?
For all those who are too busy to read fat books, yet nonetheless seek a conduit to the cosmos. Preface.
The preface.
In recent years, no more than a week goes by without news of a cosmic discovery worthy of banner headlines. While media gatekeepers may have developed an interest in the universe, this rise in coverage likely comes from a genuine increase in the public's appetite for science. Evidence for this abounds, from hit television shows inspired or informed by science, to the success of science fiction films starring marquee actors and brought to the screen by celebrated producers and directors.
Yeah, so basically he's saying that people are now starting to get a knack for space and all that fun stuff up in the sky. Science is taking over a little bit now, and people are interested to hear this, so, and I definitely am, so. Even though I already heard this before, but I've kind of forgotten about the first hour of the book already, so, yeah, I'm just gonna try and let it sink in so I can understand it fully.
And lately, theatrical release biopics featuring important scientists have become a genre unto itself. There's also widespread interest around the world in science festivals, science fiction conventions, and science documentaries for television. The highest...
Yeah, so over here in Australia we have the Parkes telescope, which I haven't been to yet, even though I only live like 2 hours away from it. And they hold events for people to come in and look at the telescope and see data and like all. I don't know fully what it has, but apparently it's a big thing, and I've wanted to go and see it, and I plan to go see it next time I'm down that way. But for me to go see it now, it's like a 10-hour drive nearly. So all in due time.
grossing film of all time is by a famous director who set a story on a planet orbiting a distant star.
It's Avatar?
And it features a famous actress who plays an astrobiologist. While most branches of science have ascended in this era,
Good movie.
the field of
The
astrophysics
first one.
persistently rises to the
I
top.
haven't seen the second one yet.
I think I know why. At one time or another, every one of us has looked up at the night sky and wondered, what does it all mean? How does it all work? And
Yep.
what is my place in the universe?
I definitely have.
If you're too busy to absorb the cosmos via classes, textbooks, or documentaries, and you nonetheless seek a brief but meaningful introduction to the field, I offer you Astrophysics for people in a hurry. In this slim volume, you will earn a foundational fluency
And it
in
is
all the
slim.
major ideas and discoveries that drive our modern understanding of the universe. If I've succeeded, you'll be culturally conversant in my field of expertise, and you just may be hungry for
Doesn't
more.
tell me how many pages are in
The
this
universe
audiobook.
is under no
But-
obligation to make sense to you.
Yeah, that's a good line too. Yeah, I
Chapter
don't know how
1,
many pages it is,
The
but
greatest story
it's a very
ever
tiny
told.
book.
The world has persisted many a long year, having once been set
Just a
going
couple
into the
years.
appropriate motions. From these, everything else follows. Lucretius, 50 BC. In the beginning,
It's a fair
nearly
while ago.
14 billion years ago, all the space and all the matter and all the energy of the known universe was contained in a volume less than 1/trillionth the size of the period that ends this sentence.
That is insane too. A trillionth of size. Like, you wouldn't even see a bit of ink from that period. that's crazy. Like, it's such an insane number to fathom. It's hard for me to fathom a million. Like, if I had a million, I don't know, cans of beer, for example, I reckon that'd be quite a few. Wouldn't know where to store them. But it's like an insane amount to think about, let alone a billion or a trillion.
Conditions were so hot, the basic forces of nature that collectively described the universe were unified. Though still unknown how it came into existence, this sub-pinpoint-sized cosmos could only expand rapidly in what today
Very
we call
rapidly.
the Big Bang. Einstein's general theory of relativity, put forth in 1916, gives us our modern understanding of gravity, in which the presence of matter and energy curves the fabric of space and time surrounding it. In the 1920s, quantum mechanics would be discovered, providing a modern
1920s,
account
wow.
of all that is small, molecules,
That's
atoms,
crazy.
and subatomic particles.
I thought it was way later
But these
than that.
two understandings of nature are formally incompatible with one another, which set physicists off on a race to blend the theory of the small with the theory of the large into a single coherent theory of quantum gravity.
I think
Although we
Stephen
haven't yet
Hawking tried to. Was it Steve? No, it was Einstein. He tried to like work out a perfect maths problem to join both the theory of the small and the theory of the large together, because one theory of relativity and I can't remember the other one, but one works for the super small and one works for the super large, and if they get too close together, it just doesn't. The maths just doesn't add up, apparently. So there's still something that we don't fully understand about where we are and how we got here.
reach the finish line, we know exactly where the high hurdles are. One of them is during the Planck era of the early universe. That's the interval of time from t equals 0 up to t equals 10 to the minus 43 seconds. 1/10 million trillion trillionths of a second after the beginning. And
that's
before
crazy.
the universe grew to 10 to the minus 35 meters, 100 billion trillion
10 to the
trillionths
minus.
of a meter across. The German physicist Max Planck, after whom these unimaginably small quantities are named, introduced the idea of quantized energy in 1900 and is generally credited as the father of quantum mechanics.
Oh wow! So
The class
he said quantum mechanics was discovered in 1920, but this Max Planck guy was in the 1900s, like early 1900s, before 1920, I'd imagine. Otherwise, he would have said 1920. So it took a little bit of time before we actually knew just what the hell Max was talking about.
Between gravity and quantum mechanics poses no practical problem for the contemporary universe. Astrophysicists apply the tenets and tools of general relativity and quantum mechanics to very different classes of problems. But in the beginning, during the Planck era, the large was small, and we suspect there must have been a kind of shotgun wedding between the two. Alas, the vows exchanged during that ceremony continue to elude us, and so no known laws of physics describe with any confidence the behavior of the universe over that time. We nonetheless expect that by the end of the Planck era, gravity wriggled loose from the other still unified forces of nature, achieving an independent identity nicely described by our current theories. As the universe aged through 10 to the minus 35 seconds, it continued to
10
expand,
to the minus
diluting
35.
all concentrations of energy, and what remained of the unified forces split into the electroweak and the strong nuclear forces. Later still, the electroweak force split into the electromagnetic and the weak nuclear forces, laying bare the four distinct forces we have come to know and love. With the weak force controlling radioactive decay,
gravity,
the strong
and
force binding the atomic nucleus, the electromagnetic force binding molecules, and gravity binding bulk matter. A trillionth of a second has passed since the beginning.
It's so tiny.
All the while, the interplay of matter in the form of subatomic particles and energy in the form of photons, massless vessels of light energy that are as much waves as they are particles, was incessant. The universe was hot enough for these photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilate, returning their energy back to photons.
Just go boom.
Yes, antimatter is real, and we discovered it, not science fiction writers. These transmogrifications are entirely prescribed by Einstein's most famous equation,
E equals
E
MC
equals
squared.
mc squared,
Which
which is a two-way recipe
energy equals mass times acceleration, I believe.
for how much matter your
Or
energy is
acceleration
worth
squared.
and how much energy your matter is worth. The c squared is the speed of light squared, a
Okay.
huge number which, when multiplied by the
Wait, I did F equals ma, not E equals MC squared. God damn it.
mass, reminds us how much energy you actually get in this exercise. Shortly before, during, and after the strong and electroweak forces parted company, the universe was a seething soup of quarks, leptons, and their antimatter siblings, along with bosons, the particles that enable their interactions. None of these particle families is thought to be divisible into anything smaller or more basic, though each comes in several varieties. The ordinary photon is a member of the boson family. The leptons most familiar to the non-physicist are the electron and perhaps the neutrino. And the most familiar quarks are, well, there are no familiar quarks.
Aren't there 6
Each of their
flavors
6
or something?
subspecies
Yeah.
has been assigned an abstract name that serves no real philological, philosophical, or pedagogical purpose.
It's like up, down, top, bottom, and I can't remember the other two.
Except to distinguish it from others. Up and down, strange and charmed,
Strange and
and
charmed.
top and bottom. Bosons, by the way, are named for the Indian scientist Satyendra Nath Bose. The word lepton derives from the Greek leptos, meaning light or small. Quark, however, has a literary and far more imaginative origin. The physicist Murray Gell-Mann, who in 1964 proposed the existence of quarks as the internal constituents of neutrons and protons, and who, at the time, thought the quark family had only 3 members, drew the name from a characteristically elusive line in James Joyce's Finnegan's Wake.
Yeah, I thought it was from
3
a book.
quarks for muster mark. One thing quarks
Okay,
do
so I
have
do
going
remember
for them,
some things.
all their names are simple. Something chemists, biologists, and especially geologists seem incapable of achieving when naming their own stuff. Quarks are quirky beasts. Unlike protons, each with an electric charge of +1, and electrons with a charge of -1, quarks have fractional charges that come in thirds.
Oh, wow.
And you'll never catch a quark all by itself. It will always be clutching other quarks nearby. In fact, the force that keeps two or more of them together actually grows stronger the more you separate them, as if they were attached by some
like a
sort
rubber
of
band.
subnuclear rubber band.
Yeah.
Separate the quarks enough, the rubber band snaps, and the stored energy summons E equals mc squared to create a new quark at each end, leaving you back where you started.
Okay, so that's interesting. So if like two quarks together, and let's say you could pull them apart, other quarks are just made up out of nothing. They just have to be paired up, so there'll be more. So I wonder if that's how quarks kind of multiplied back at the Big Bang or whatever. So like they got separated with the explosion, and then they had to create other quarks from whatever matter we don't know yet. And then that, like, obviously quarks are like the building blocks to protons, electrons, neutrons, and then it goes further up. So maybe that's how matter sort of kind of started. Like, I know antimatter and matter have another play in it too, but that's mind-blowing. That these quarks have to create a pair. That's interesting.
During the quark-lepton era, the universe was dense enough for the average separation between unattached quarks to rival the separation between attached quarks. Under those conditions, allegiance between adjacent quarks could not be unambiguously established, and they moved freely among themselves, in spite of being collectively bound to one another. The discovery of this state of matter, a kind of quark cauldron, was reported for the first time in 2002 by a team of physicists at the Brookhaven National Laboratories, Long Island, New York. Strong theoretical evidence suggests that an episode in the very early universe, perhaps during one of the force splits, endowed the universe with a remarkable asymmetry, in which particles of matter barely outnumbered particles of antimatter.
Yeah, so
By
I wonder
about
if
a
quarks
billion
had
and
an
one to a billion.
issue to do with
That
that as
small
well.
difference in population would hardly get noticed by anybody amid the continuous creation, annihilation, and recreation of quarks and antiquarks, electrons and anti-electrons, better known as positrons, and neutrinos and antineutrinos. The odd man out had oodles of opportunity to find somebody to annihilate with, and so did everybody else. But not for much longer. As the cosmos continued to expand and cool, growing larger than the size of our solar system, the temperature dropped rapidly, below 1 trillion degrees Kelvin.
Still pretty warm.
A millionth of a second has passed since the beginning.
So what? Hang on. He just said it grew beyond the size of our solar system alone, within 1/1,000,000th of a second of this Big Bang happening. These are numbers that I just can't fathom. That's moving bloody quick. Really, really quick.
This tepid universe was no longer hot enough or dense enough to cook quarks, and so they all grabbed dance partners, creating a permanent new family of heavy particles called hadrons, from the Greek hadros,
Hadron
meaning
Collider.
thick.
That's what
That
they
quark
use.
to hadron transition soon resulted in the emergence of protons and neutrons, as well as other less familiar heavy particles, all composed of various combinations of quark species. In Switzerland, back on Earth, the European Particle Physics Collaboration, CERN, uses a large accelerator to collide beams of hadrons in an attempt to recreate
The
these
LHC.
very conditions. This largest machine in the world is sensibly called the Large Hadron Collider. The slight matter-antimatter
I think everyone
asymmetry
knows about that
afflicting
machine.
the quark-lepton soup now passed to the hadrons, but with extraordinary consequences. As the universe continued to cool, the amount of energy available for the spontaneous creation of basic particles dropped. During the Hadron era, ambient photons could no longer invoke E equals mc squared to manufacture quark-antiquark pairs. Not only that, the photons that emerged from all the remaining annihilations lost energy to the ever-expanding universe, dropping below the threshold required to create hadron-antihadron pairs. For every billion annihilations, leaving 1 billion photons in their wake, a single hadron survived.
Oh, wow.
Those loners would get to have all the fun, serving as the ultimate
How do
source
they
of
work
matter
that
to
out,
create
though?
galaxies,
Like, how do we know
stars,
that that's the
planets,
right number?
and petunias. Without the billion and one to a billion imbalance between matter and antimatter, all mass in the universe would have self-annihilated, leaving a cosmos made of photons
Just empty.
and nothing else.
Yeah, we wouldn't
The
be here.
ultimate let there be light scenario.
That's like a perfect,
By now, 1
perfect
second
video
of
to
time
pop
has
up during
passed.
that part. 1 second has
The
passed.
universe has grown to a few light years across, about the distance from the sun to its closest neighboring stars.
Which is
At a billion degrees, it's still plenty hot and still able to cook electrons, which, along with their positron counterparts, continue to pop in and out of existence. But in the ever-expanding, ever-cooling universe, their days, seconds really, are numbered. What was true for quarks and true for hadrons had become true for electrons. Eventually, only 1 electron in a billion survives.
Wow.
The rest annihilate with positrons, their antimatter sidekicks, in a sea of photons. Right about now, 1 electron for every proton has been frozen into existence. As the cosmos continues to cool, dropping below 100 million degrees, protons
Still
fuse
hot.
with other protons as well as with neutrons, forming atomic nuclei and hatching a universe in which 90% of these nuclei are hydrogen and 10% are helium, along with trace amounts of deuterium, heavy
Lithium.
hydrogen, tritium, even heavier hydrogen, and lithium.
Yeah, I thought lithium was there.
2 minutes
that's
have
what
now
I-
passed
that's what
since
I
the
remember.
beginning.
Okay, so we went from 1 second to 2 minutes, which is a fairly long time change. But from what I remember hearing about at school was that when the Big Bang was created, all we had was hydrogen, helium, and lithium. And that's what made the first stars, which are stupidly named Population 3 stars. You'd think they'd be called Population 1 stars, but they're not. And that's what fueled the heavier elements once they blew up into supernovas and stuff like that.
For another 380,000 years, not much will happen to our particle soup. Throughout these millennia, the temperature remains hot enough for electrons to roam free among the photons, batting them to and fro as they interact with one another. But this freedom comes to an abrupt end when the temperature of the universe falls below 3,000 degrees Kelvin, about half the temperature of the sun's surface.
Right, yeah,
And all
we're
the free
starting to get a bit
electrons
cooler.
combine with nuclei. The marriage leaves behind a ubiquitous bath of visible light, forever imprinting the sky with a record of where all the matter was in that moment, and completing the formation of particles and atoms in the primordial universe. For the first billion years, the universe continued to expand and cool as matter gravitated into the massive concentrations we call galaxies. Nearly 100 billion of them formed, each containing hundreds of billions of
insane.
stars that undergo thermonuclear fusion in their
That's
cores.
so hard to
Those
fathom.
stars, with more than about 10 times the mass of the sun, achieve sufficient pressure and temperature in their cores to manufacture dozens of elements heavier than hydrogen, including those that
This is
compose
why I like
planets
space.
and whatever
'Cause
life
it's
can thrive upon them.
So freaking crazy, man.
These elements would be stunningly useless were they to remain where they formed, but high-mass stars fortuitously explode, scattering their chemically enriched guts throughout the galaxy. After 9 billion years of such enrichment in an undistinguished part of the universe, the outskirts of the Virgo supercluster, in an undistinguished galaxy, the Milky Way, in an undistinguished region, the Orion Arm, an undistinguished star, the Sun.
Is
was
that
born.
us? Are we on the Orion?
The
Arm?
gas cloud from which the sun formed contained a sufficient supply of heavy elements to coalesce and spawn a
didn't know
complex inventory of orbiting objects that includes several rocky and gaseous planets, hundreds of thousands of asteroids, and billions of comets. For the first several 100 million years, large quantities of leftover debris in wayward orbits would accrete onto larger bodies. This occurred in the form of high-speed, high-energy impacts, which rendered molten the surfaces of the rocky planets, preventing the formation of complex molecules. As less and less
too
accretable matter remained in the solar system, planet surfaces began to cool. The one we call Earth formed in a kind of Goldilocks zone around the sun,
Third rock
where
from the
oceans
sun.
remain largely in liquid form.
Not too hot and not too
Had
cold.
Earth been much closer to the sun, the oceans would have evaporated, Had Earth been much farther away, the oceans would have frozen. In either case, life as we know it would not have evolved. Within the chemically rich
Lucky.
liquid oceans, by a mechanism yet to be discovered, organic molecules transitioned to self-replicating life. Dominant in this primordial soup were simple anaerobic bacteria.
I can't believe we're only 17, nearly 18 minutes in, and he's already done the whole Big Bang, and we're on to life on Earth. Imagine if he wrote a book called Astrophysics for People Not in a Hurry, how long that would be. And I would be down to listen to that audiobook as well, because that would have so much more detail into it.
That thrives in oxygen-empty environments, but excretes chemically potent oxygen as one of its byproducts. These early single-celled organisms unwittingly transformed Earth's carbon dioxide-rich atmosphere into one with sufficient oxygen to allow aerobic organisms to emerge and dominate the oceans and land. These same oxygen atoms, normally found in pairs, O2, also combined in threes to form ozone, O3, in the upper atmosphere, which serves as a shield that protects Earth's surface from most of the sun's molecule-hostile ultraviolet photons. We owe the remarkable diversity of life on Earth, and we presume elsewhere in the universe, to the cosmic abundance of carbon and the countless number of simple and complex molecules that contain it. There is no doubt about it. More varieties of carbon-based molecules exist than all other kinds of molecules combined. But life is fragile. Earth's occasional encounters with large, wayward comets and asteroids, a formerly common event, wreaks intermittent havoc upon our ecosystem. A mere 65 million years ago, less than 2% of Earth's
dinosaurs.
A 10 trillion-ton asteroid hit what is now the Yucatan Peninsula and obliterated more than 70% of Earth's flora and fauna, including all the famous outsized dinosaurs. Extinction. This ecological catastrophe enabled our mammal ancestors to fill freshly vacant niches rather than continue to serve as hors d'oeuvres for T-Rex. One big-brained branch of these mammals, that which we call primates, evolved a genus and species, Homo sapiens, with sufficient intelligence to invent methods and tools of science, and to deduce the origin and evolution of the universe.
Damn.
What happened before all this? What happened before the beginning? Astrophysicists have no idea, or rather, our most creative ideas have little or no grounding in experimental science. In response, some religious people assert, with a tinge of righteousness,
it's God.
That something must have started it all, a force greater than all others,
a
source from which everything issues, a prime mover. In the mind of such a person, that something is, of course, God. But what if the universe was always there, in a state or condition we have yet to identify? A multiverse, for instance, that continually births universes. Or what if the universe just popped into existence from nothing? Or what...
Even like the multiverse theory is like mind-boggling. All this is mind-boggling, but the multiverse as well, like there's multiple universes of you doing anything and everything in your own, like anything possible, and this is the one that only us can understand, and this is the part of the universe, or the one universe where we're stuck doing what we're doing. Imagine if, like, in another universe you were like a celebrity, or you got murdered by George W. Bush or something like that. Like, there's multiple different things that could happen. Like, Cat in the Hat is real. Like, it could just infinitely go beyond logic, and it's just too hard to comprehend.
If everything we know and love were just a computer simulation rendered for entertainment by a superintelligent alien species. These philosophically fun ideas usually satisfy nobody.
Yeah.
Nonetheless, they remind us that ignorance is the natural state of mind for a research scientist. People who believe they are ignorant of nothing have neither looked for nor stumbled upon the boundary between what is known and unknown in the universe. What we do know, and what we can assert without further hesitation, is that the universe had a beginning. The universe continues to evolve.
Yes.
And yes, every one of our body's atoms is traceable to the Big Bang and to the thermonuclear furnaces within high-mass stars that exploded more than 5 billion years ago.
So we're all made of
We are
stardust.
stardust brought to
Oh my
life,
God.
then empowered by the universe to figure itself out. And we have only
That's
just
funny.
begun.
So that was chapter 1?
Chapter 2,
Yeah.
On Earth as in the Heavens. Until Sir Isaac Newton wrote down the universal law of gravitation, nobody had any reason to presume that the laws of physics at home were the same everywhere else in the universe. Earth had earthly things going on, and heavens had heavenly things going on. According to Christian teachings of the day, God controlled the heavens, rendering them unknowable to our feeble mortal minds. When Newton breached this philosophical barrier by rendering all motion comprehensible and predictable, some theologians criticized him for leaving nothing for the Creator to do. Newton had figured out that the force of gravity pulling ripe apples from their orchards also guides tossed objects along their curved trajectories and directs the moon in its orbit around Earth.
I mean,
Newton's law of gravity.
we all know that now, but back then it would have been like, oh my God, I finally worked this out. And I think we only know it because we've been taught about it. Not so much that... I don't think I've ever met any individual who's like 2 or 3 years old who worked out that gravity is the same, like if you throw a ball or something like that.
Also guides planets, asteroids, and comets in their orbits around the Sun, and keeps hundreds of billions of stars in orbit within our Milky Way galaxy. This universality of physical laws drives scientific discovery like nothing else. And gravity was just the beginning. Imagine the excitement among 19th century astronomers when laboratory prisms, which break light beams into a spectrum of colors, were first turned to the Sun.
They're really cool too.
Spectra are not only beautiful, but contain oodles of information about the light-emitting object, including its temperature and composition.
That's how we
Chemical
find
elements
planets around
reveal
other
themselves
stars.
by their unique patterns of light or dark bands that cut across the spectrum. To people's delight and amazement, the chemical signatures on the Sun were identical to those in the laboratory. No longer the exclusive tool of chemists, the prism showed that as different as the Sun is from Earth in size, mass, temperature, location, and appearance,
It's all the same.
we both contain the same stuff.
Mm-hmm.
Hydrogen, carbon, oxygen, nitrogen, calcium, iron, and so forth. But more important than our laundry list of shared ingredients was the recognition that the laws of physics prescribing the formation of these spectral signatures on the Sun were the same laws operating on Earth, 93 million miles away. So fertile was this concept of universality that it was successfully applied in reverse. Further analysis of the Sun's spectrum revealed the signature of an element that had no known counterpart on Earth. Being of the Sun, the new substance was given a name derived from the Greek word helios, the Sun,
Helium.
and was only later discovered in the lab. Thus, helium became the first and only element in the chemist's periodic table to be discovered someplace other than Earth.
Really? Wow, that's
the laws of
interesting.
physics work in the solar system, but
Because, like, we have helium balloons and shit like that, but for them to, like, this is going back way before we even probably farmed helium from the mines and all that, or from pockets in the ground. That's insane, because, like, we knew that there was, like, carbon, oxygen, all that, before we knew about helium, which is number 1 on the periodic table. Wow. No, helium is 2, hydrogen is 1.
do they work across the galaxy, across the universe, across time itself? Step by step, the laws were tested. Nearby stars also revealed familiar chemicals. Distant binary stars, bound in mutual orbit, seem to know all about Newton's laws of gravity. For the same reason, so do binary galaxies. And like the geologist's stratified sediments, which serve as a timeline of earthly events, the farther away we look in space, the further back in time we see. Spectra from the most distant objects in the universe show the same chemical signatures that we see nearby in space and in time. True, heavy elements were less abundant back then. They are manufactured primarily in subsequent generations of exploding stars. But the laws describing the atomic and molecular processes that created these spectral signatures remain intact. In particular, a quantity known as the fine structure constant, which controls the basic fingerprinting for every element, must have remained unchanged for billions of years. Of course, not all things and phenomena in the cosmos have counterparts on Earth. You've probably never walked through a cloud of glowing million-degree plasma, and I'd bet you've never greeted a black hole on the street. What matters is the universality of the physical laws that describe them. When spectral analysis was first applied to the light emitted by interstellar nebulae, a signature was discovered that, once again, had no counterpart on Earth.
Really?
At the time, the periodic table of elements had no obvious place for a new element to fit. In response, astrophysicists invented the name nebulium as a placeholder until they could figure out what was going on.
I don't know.
Turned out that in space, gaseous nebulae are so rarefied that atoms go long stretches without colliding. Under these conditions, electrons can do things within atoms that had never before been seen in Earth labs. Nebulium was simply the signature of ordinary oxygen doing extraordinary things. This universality of physical laws tells us that if we land on another planet with a thriving alien civilization, they will be running on the same laws that we have discovered and tested here on Earth, even if the aliens harbor different social and political beliefs.
Yeah.
Furthermore, if you want to talk to the aliens, you can bet they don't speak English or French or even Mandarin. Nor would you know whether shaking their hands, if indeed their outstretched appendage is a hand, would be considered an act of war or peace. Your best hope is to find a way to communicate using the language of science.
Yeah.
Such an attempt was made in the 1970s.
That's what they did with messages on the gold disc, like to be able to read it and all that stuff. It was all applied in science, like how to play back the the golden record, and as well with the message sent from, I believe, the Arecibo telescope to somewhere in space. Was it Proxima? I think it might have been Proxima. And it was just like a whole bunch of science stuff that they could depict and learn, or hopefully depict that. But they probably won't even see it.
With Pioneer 10 and 11 and Voyager 1 and 2. All 4 spacecraft were endowed with enough energy after gravity assist from the giant planets to escape the solar system entirely. Pioneer wore a golden-etched plaque that showed in scientific pictograms the layout of our solar system, our location in the Milky Way galaxy, and the structure of the hydrogen atom. Voyager went further and also included a gold record album containing diverse sounds from Mother Earth, including the human heartbeat, whale songs, and musical selections from around the world, including the works of Beethoven and Chuck Berry. While this humanized the message, it's not clear whether alien ears would have a clue what they were listening to, assuming they have ears in the first place. My favorite parody of this gesture was a skit on NBC's Saturday Night Live, shortly after the Voyager launch, in which they showed a written reply from the aliens who recovered the spacecraft. The note simply requested, "Send more Chuck Berry." Science thrives not only on the universality of physical laws, but also on the existence and persistence of physical constants. The constant of gravitation, known by most scientists as Big G, supplies Newton's equation of gravity with the measure of how strong the force will be. This quantity has been implicitly tested for variation over eons. If you do the math, you can determine that a star's luminosity is steeply dependent on Big G. In other words, if Big G had been even slightly different in the past, then the energy output of the sun would have been far more variable than anything the biological, climatological, or geological records indicate. Such
right.
is the uniformity of our universe.
Gee.
Among all constants, the speed of light is the most famous. No matter how fast you go, you will never overtake a beam of light.
Yeah.
Why
so
not?
I think that's
No
the
experiment ever conducted has ever revealed an object of any form reaching the speed of light. Well-tested laws of physics predict and account for that fact. I know these statements sound close-minded. Some of the most boneheaded science-based proclamations in the past have underestimated the ingenuity of inventors and engineers. We will never fly. Flying will never be commercially feasible. We will never split the atom. We will never break the sound barrier. We will never go to the moon. What they have in common is that no established law of physics stood in their way. The claim we will never outrun a beam of light is a qualitatively different prediction. It flows from basic time-tested physical principles. Highway signs for interstellar travelers of the future will justifiably read, "The speed of light. It's not just a good idea, it's the law." Unlike getting caught speeding on Earth roads, the good thing about the laws of physics is that they require no law enforcement agencies to maintain them. Although, I did once own a geeky t-shirt that proclaimed, "Obey gravity." All measurements suggest that the known fundamental constants and the physical laws that reference them are neither time-dependent nor location-dependent. They're truly constant and universal. Many natural phenomena manifest multiple physical laws operating at once. This fact often complicates the analysis and in most cases requires high-performance computing to calculate what's going on and to keep track of important parameters. When comet Shoemaker-Levy 9 plunged into Jupiter's gas-rich atmosphere
Yes,
in
I
July
remember hearing about
1994 and then exploded, the most accurate computer model combined the laws of fluid mechanics, thermodynamics, kinematics, and gravitation.
This is 94.
Climate and weather represent other leading examples of complicated and difficult-to-predict phenomena, but the basic laws governing them are still at work. Jupiter's Great Red Spot, a raging anticyclone that's been going strong for at least 350 years, is driven by identical physical processes that generate storms on Earth and elsewhere in the solar system. Another class of universal truths is the conservation laws, where the amount of some measured quantity remains unchanged no matter what. The three most important are the conservation of mass and energy, the conservation of linear and angular momentum, and the conservation of electric charge. These laws are in evidence on Earth and everywhere we have thought to look, from the domain of particle physics to the large-scale structure of the universe. In spite of this boasting, all is not perfect in paradise. It happens that we cannot see, touch, or taste the source of 85% of the gravity we measure in the universe.
Yeah.
This mysterious dark matter, which remains undetected except for its gravitational pull on matter we see, may be composed of exotic particles that we have yet to discover or identify.
That's what I reckon as well. Like, we give it the name dark matter, which is fine. And we know it's there. We just can't see it or interact with it, but we know it's there based on its influence on other things around. So, what I agree with Neil on this is that we just haven't worked out how to actually understand that particle or whatever it is, and all in due time. Maybe tomorrow, maybe 10 years, maybe 1,000 years, who knows?
A small minority of astrophysicists, however, are unconvinced and have suggested that there is no dark matter. You just need to modify Newton's law of gravity.
I mean, that
Simply
could also
add
be
a few
the case.
components to the equations, and all will be well. Perhaps one day we will learn that Newton's gravity indeed requires adjustment. That'll be okay. It has happened once before. Einstein's 1916 general theory of relativity expanded on the principles of Newton's gravity in a way that also applied to objects of extremely high mass. Newton's law of gravity breaks down in this expanded realm, which was unknown to him. The lesson here is that our confidence flows through the range of conditions over which a law has been tested and verified. The broader that range, the more potent and powerful the law becomes in describing the cosmos. For ordinary household gravity, Newton's law works just fine. It got us to the moon and returned us safely to Earth in 1969. For black holes in the large-scale structure of the universe, we need general relativity. And if you insert low mass and low speeds into Einstein's equations, they literally, or rather mathematically, become Newton's equations. All good reasons to develop confidence in our understanding and of all we claim to understand. To the scientist, the universality of physical laws makes the cosmos a marvelously simple place. By comparison, human nature, the psychologist's domain, is infinitely more daunting. In America, local school boards vote on subjects to be taught in the classroom. In some cases, votes are cast according to the whims of cultural, political, or religious tides. Around the world, varying belief systems lead to political differences that are not always resolved peacefully. The power and beauty of physical laws is that they apply everywhere, whether or not you choose to believe in them. In other words, after the laws of physics, everything else is opinion. Not that scientists don't argue, we do, a lot. But when we do, we typically express opinions about the interpretation of insufficient or ratty data on the bleeding frontier of our knowledge. Wherever and whenever a physical law can be invoked in the discussion, the debate is guaranteed to be brief. No, your idea for a perpetual motion machine will never work. It violates well-tested laws of thermodynamics. No, you can't build a time machine that will enable you to go back and kill your mother before you were born. It violates causality laws. And without violating momentum laws, you cannot spontaneously levitate and hover above the ground, whether or not you are seated in the lotus position.
I mean, Neo did.
You could, in principle, perform this stunt if you managed to let forth a powerful and sustained exhaust of flatulence.
Just fire you
Knowledge
out.
of physical laws can, in some cases, give you the confidence to confront surly people. A few years ago, I was having a hot cocoa nightcap at a dessert shop in Pasadena, California. Ordered it with whipped cream, of course. When it arrived at the table, I saw no trace of the stuff. After I told the waiter that my cocoa had no whipped cream, he asserted I couldn't see it because it sank to the bottom. But whipped cream has low density and floats on all liquids that humans consume. So I offered the waiter two possible explanations. Either somebody forgot to add the whipped cream to my hot cocoa, or the universal laws of physics were different in his restaurant. Unconvinced, he defiantly brought over a dollop of whipped cream to demonstrate his claim. After bobbing once or twice, the whipped cream rose to the top, safely afloat. What better proof do you need of the universality of physical law?
Yes, sir. Proved him right with a bit of whipped cream.
Chapter 3. Let There Be Light. After the Big Bang, the main agenda of the cosmos was expansion, ever diluting the concentration of energy that filled space. With each passing moment, the universe got a little bit bigger, a little bit cooler, and a little bit dimmer. Meanwhile, matter and energy co-inhabited a kind of opaque soup in which free-range electrons continually scattered photons every which way. For 380,000 years, things carried on that way. In this early epoch, photons didn't travel far before encountering an electron. Back then, if your mission had been to see across the universe, you couldn't. Any photon you detected had careened off an electron right in front of your nose, nano and picoseconds earlier, a billionth and a trillionth of a second. Since that's the largest distance that information can travel before reaching your eyes, the entire universe was simply a glowing opaque fog in every direction you looked. The sun and all other stars behaved this way too. As the temperature drops, particles move more and more slowly, and so right about then, when the temperature of the universe first dipped below a red-hot 3,000 degrees Kelvin, electrons slowed down just enough to be captured by passing protons, thus bringing full-fledged atoms into the world. This allowed previously harassed photons to be set free and travel on uninterrupted paths across the universe. This cosmic background is the incarnation of the leftover light from a dazzling, sizzling early universe and can be assigned a temperature based on what part of the spectrum the dominant photons represent. As the cosmos continued to cool, the photons that had been born in the visible part of the spectrum lost energy to the expanding universe and eventually slid down the spectrum, morphing into infrared photons.
Yeah, right.
Although the visible light photons had become weaker and weaker, they never stopped being photons. What's next on the spectrum? Today, the universe has expanded by a factor of 1,000 from the time photons were set free. And so
Comes up
the
to
cosmic
infrared,
background
ultraviolet.
has in turn cooled by a factor of 1,000. All the visible light photons from that epoch have become 1/1000th as energetic. They're now microwaves, which is where we derive the modern moniker cosmic microwave background, or CMB for short.
Yeah.
Keep this up, and 50 billion years from now, astrophysicists will be writing about the cosmic radio wave background. When something glows from being heated, it emits light in all parts of the spectrum, but will always peak somewhere. For household lamps that still use glowing metal filaments, the bulbs all peak in the infrared, which is the single greatest contributor to their inefficiency as a source of visible light. Our senses detect infrared only in the form of warmth on our skin.
Yeah.
The LED revolution in advanced lighting technology creates pure visible light without wasting wattage on invisible parts of the spectrum. That's how you can get crazy-sounding sentences on packaging, like 7 watts LED replaces 60 watts incandescent. Being the remnant of something that was once brilliantly aglow, the CMB has the profile we expect of a radiant but cooling object. It peaks in one part of the spectrum, but radiates in other parts of the spectrum as well. In this case, besides peaking in microwaves, the CMB also gives off some radio waves and a vanishingly small number of photons of higher energy.
Yeah.
In the mid-20th century, the subfield of cosmology, not to be confused with cosmetology, didn't have much data. And where data are sparse, competing ideas abound that are clever and wishful. The existence of the CMB was predicted by the Russian-born American physicist George Gamow and colleagues during the 1940s. The foundation of these ideas came from the 1927 work of the Belgian physicist and priest Georges Lemaitre, who is generally recognized as the father of Big Bang cosmology. But it was American physicists Ralph Alpher and Robert Herman who, in 1948, first estimated what the temperature of the cosmic background ought to be. They based their calculations on 3 pillars. 1. Einstein's 1916 general theory of relativity. 2. Edwin Hubble's 1929 discovery that the universe is expanding. And 3. Atomic physics developed in laboratories before and during the Manhattan Project that built the atomic bombs of World War II. Herman and Alpher calculated and proposed a temperature of 5 degrees Kelvin for the universe. Well, that's just plain wrong. The precisely measured temperature of these microwaves is 2.725 degrees, sometimes written as simply 2.7 degrees. And if you're numerically lazy, nobody will fault you for rounding the temperature of the universe to 3 degrees. Let's pause for a moment. Herman and Alpher used atomic physics, freshly gleaned in a lab, and applied it to hypothesized conditions in the early universe. From this, they extrapolated billions of years forward, calculating what temperature the universe should be today. That their prediction even remotely approximated the right answer is a stunning triumph of human insight. They could have been off by a factor of 10 or 100, or they could have predicted something that isn't even there. Commenting on this feat, the American astrophysicist J. Richard Gott noted, predicting that the background existed and then getting its temperature correct to within a factor of 2 was like predicting that a flying saucer 50 feet wide would land on the White House lawn, but instead, a flying saucer 27 feet wide actually showed up.
Yeah, that's pretty crazy back in that day. Like he said, early 20th century, so that's like 1950s, something like that. And for them to get that close is absolutely insane. Like they know their maths and they did it, and I mean they were off by a factor of 2, not 10 or 1,000 or 100 like what Neil said. So That's wow. It's just mind-boggling that some people are this smart and can work out all those sorts of things. Crazy.
The first direct observation of the cosmic microwave background was made inadvertently in 1964 by American physicists Arno Penzias and Robert Wilson of Bell Telephone Laboratories, the research branch of AT&T. In the 1960s, everyone knew about microwaves, but almost no one had the technology to detect them. Bell Labs, a pioneer in the communications industry, developed a beefy horn-shaped antenna for just that purpose. But first, if you're going to send or receive a signal, you don't want too many sources contaminating it. Penzias and Wilson sought to measure background microwave interference to their receiver to enable clean, noise-free communication within this band of the spectrum.
So this is the same way like telescopes work. Like at the old, now gone Arecibo one that collapsed, the people who lived around it weren't allowed to use phones or even petrol-fueled cars. They all had to have diesel cars for some reason. Apparently there was like some interference with signal to the telescope. So, and it's the same in parks where I am, or where in Australia where I live. There is a video I watched the other day of someone who went to go there and talk about the telescope, and he had wireless or a wired microphone on his chest, and he said he wouldn't be allowed this, but it was a maintenance day, so they were allowed to be hooked up for all that. So it's pretty crazy. Like, you can't have any mobile activity or anything. Like, it has to be a very quiet area if you're searching for places out in space. So it's very, very cool, and I think I could live with that.
They were not cosmologists. They were techno-wizards honing a microwave receiver and unaware of the gamma of Herman and alpha predictions. What Penzias and Wilson were decidedly not looking for was the cosmic microwave background. They were just trying to open a new channel of communication for AT&T. Penzias and Wilson ran their experiment and subtracted from their data all the known terrestrial and cosmic sources of interference they could identify. But one part of the signal didn't go away, and they just couldn't figure out how to eliminate it. Finally, they looked inside their antenna and saw pigeons nesting there. They were worried that a white dielectric substance, pigeon poop, might be responsible for the signal, because they detected it no matter what direction the detector pointed. After cleaning out the dielectric substance, the interference dropped a little bit, but a leftover signal remained. The paper they published in 1965 was all about this unaccountable excess antenna temperature. Meanwhile, a team of physicists at Princeton, led by Robert Dicke, was building a detector specifically to find the CMB. But they didn't have the resources of Bell Labs, so their work went a little slower. And the moment Dicke and his colleagues heard about Penzias and Wilson's work, the Princeton team knew exactly what the observed excess antenna temperature was. Everything fit, especially the temperature itself, and that the signal came from every direction in the sky. In 1978, Penzias and Wilson won the Nobel Prize for their discovery. And in 2006, American astrophysicists John C. Mather and George F. Smoot would share the Nobel Prize for observing the CMB over a broad range of the spectrum, bringing cosmology from a nursery of clever but untested ideas into the realm of a precision experimental science.
I only found out the other day, actually, while watching a YouTube video, that the temperature of the CMB, the cosmic microwave background, there's like hot parts and cold parts, and the only difference between the hotter parts and the colder parts is like 2 Kelvin, 3 Kelvin, which is insane because I thought it would be like, I don't know, 50 or 100 Kelvin or something like that, but it's so minusculely tiny, but they could work that out just from a telescope. It's insane, dude. Science is great. I love it.
Because light takes time to reach us from distant places in the universe, if we look out in deep space, we actually see eons back in time. So if the intelligent inhabitants of a galaxy far, far away were to measure the temperature of the cosmic background radiation at the moment captured by our gaze, they should get a reading higher than 2.7 degrees, because they are living in a younger, smaller, hotter universe than we are. Turns out you can actually test this hypothesis.
That's interesting.
The molecule cyanogen, CN, once used on convicted murderers as the active component of the gas administered by their executioners, gets excited by exposure to microwaves. If the microwaves are warmer than the ones in our CMB, they excite the molecule a little more. In the Big Bang model, the cyanogen in distant younger galaxies gets bathed in a warmer cosmic background than the cyanogen in our own Milky Way galaxy. And that's exactly what we observe. You can't make this stuff up. Why should any of this be interesting? The universe was opaque until 380,000 years after the Big Bang, so you could not have witnessed matter taking shape, even if you'd been sitting front row center. You couldn't have seen where the galaxy clusters and voids were starting to form. Before anybody could have seen anything worth seeing, photons had to travel unimpeded across the universe as carriers of this information. The spot where each photon began its cross-cosmos journey is where it had smacked into the last electron that would ever stand in its way, the point of last scatter. As more and more photons escape unsmacked, they create an expanding surface of last scatter, some 120,000 years deep. That surface is where all the atoms in the universe were born. An electron joins an atomic nucleus, and a little pulse of energy in the form of a photon soars away into the wild red yonder. By then...
Okay, so that's how we could see, because the electrons are bumping into photons, and the photons get ejected, or something similar to that. That's very interesting, because I know that photon is light and all that. But, like, it's got to be more than light, obviously, but that's what we use to track back in time and all that sort of stuff. So, to know that the only reason we can see so far back is because of the electrons that have bumped into... That's pretty freaking cool. Also, guys, if you could like this stream and try and get more people in, because that's how YouTube works, and I haven't found a stream like this before on YouTube, so I'd like more people to actually understand it and all that sort of stuff. I don't make money from this shit, I'm just doing it for fun. So, thank you, and let's keep going. But yeah, that's crazy. Electrons bumping into photons.
Some regions of the universe had already begun to coalesce by the gravitational attraction of their parts. Photons that last scattered off electrons in these regions developed a different, slightly cooler profile than those scattering off the less sociable electrons sitting in the middle of nowhere. Where matter accumulated, the strength of gravity grew, enabling more and more matter to gather. These regions seeded the formation of galaxy superclusters, while other regions were left relatively empty. When you map the cosmic microwave background in detail, you find that it's not completely smooth. It's got spots that are slightly hotter and slightly cooler than average. By studying these temperature variations in the CMB,
it's not by much.
that is to say, by studying patterns in the surface of last scatter, we can infer what the structure and content of the matter was in the early universe. To figure out how galaxies and clusters and superclusters arose, we use our best probe, the CMB, a potent time capsule that empowers astrophysicists to reconstruct cosmic history in reverse. Studying its patterns is like performing some sort of cosmic phrenology as we analyze the skull bumps of the infant universe.
I don't even know
When
what
constrained by
phrenology
other
is.
observations of the contemporary and distant universe, the CMB enables you to decode all sorts of fundamental cosmic properties. Compare the distribution of sizes and temperatures of the warm and cool areas, and you can infer how strong the force of gravity was at the time, and how quickly matter accumulated, allowing you to then deduce how much ordinary matter, and dark energy there is in the universe. From here, it's then straightforward to tell whether or not the universe will expand forever.
That's a good question. What do you guys think? Do you reckon this the universe will just keep on expanding, or will it come to an end? I think there's three ending scenarios. One's like the big rip, one's the big cold or something, and one's the big crash. Something like that. I can't remember what they are, but there's like three potential endings. And I don't know. I'm not smart enough to answer that question. But at this point, I think we're pretty safe because it's still expanding. So us humans will be fine for next trillion years or billion years or whatever it is.
Ordinary matter is what we're all made of. It has gravity and interacts with light. Dark matter is a mysterious substance that has gravity but does not interact with light in any known way.
Once everything starts
Dark
to blue
energy
shift, that's when
is a
you have to worry.
mysterious pressure in
Instead
the
of
vacuum of
redshifting.
space that acts in the opposite direction of gravity, forcing the universe to expand faster than it otherwise would. What our phrenological exam says is that we understand how the universe behaved, but that most of the universe is made of stuff about which we are clueless. Our profound areas of ignorance notwithstanding, today as never before, cosmology has an anchor because the CMB reveals the portal through which we all walked. It's a point where interest
Where
in
it all
physics
started,
happened,
yeah.
and where we learned about the universe before and after its light was set free. The simple discovery of the cosmic microwave background turned cosmology into something more than mythology. But it was the accurate and detailed map of the cosmic microwave background that turned cosmology into a modern science. Cosmologists have plenty of ego. How could you not when your job is to deduce what brought the universe into existence? Without data, their explanations were just hypotheses. Now, each new observation, each morsel of data, wields a two-edged sword. It enables cosmology to thrive on the kind of foundation that so much of the rest of science enjoys. But it also constrains theories that people thought up when there wasn't enough data to say whether they were right or wrong. No science achieves maturity without it. Chapter 4.
Alright, we're up to chapter 4. I'm just going to pause before we continue this chapter, and I just have to remind you, in case you didn't read the description, if I put it in there or not. No, I didn't. So I have to keep pausing and talking, otherwise YouTube will get mad at me and get me claimed for copyright. So, yeah, that's why I have to pause and react and talk my own stuff into the video. Sorry if it's annoying you.
Between the Galaxies. In the grand tally of cosmic constituents, galaxies are what typically get counted. Latest estimates show that the observable universe may contain 100 billion of them. Bright and beautiful and packed with stars, galaxies decorate the dark voids of space like cities across a country at night. But just how voidy is the void of space?
Voidy.
How empty is the countryside between cities? Just because galaxies are in your face, and just because they would have us believe that nothing else matters, the universe may nonetheless contain hard-to-detect things between the galaxies. Maybe those things are more interesting or more important to the evolution of the universe than the galaxies themselves. Our own spiral-shaped galaxy, the Milky Way, is named for its spilled milk appearance to the unaided eye across
I
Earth's
can't remember how
nighttime
that
sky.
name came from.
Indeed, the very word galaxy derives from the Greek galaxias, milky. Our pair of
gonna say
nearest
Greece.
neighbor galaxies, 600,000 light-years distant, are both small and irregularly shaped. Ferdinand Magellan's ship's log identified these cosmic objects during his famous round-the-world voyage of 1519. In his honor, we call them the Large and Small Magellanic Clouds, and they're visible primarily from the southern hemisphere as a pair of cloud-like splotches on the
Yep.
sky, parked beyond the stars.
That's the beauty of
nearest
Australia. We can see it. Kind of. I've seen it. Through telescopes and all that. It's pretty cool.
Galaxy larger than our own is 2 million light-years away beyond the stars that trace the constellation Andromeda. This spiral galaxy, historically dubbed the Great Nebula in Andromeda, is a somewhat more massive and luminous twin of the Milky Way.
Or at least I think
Notice
I've
that the
seen
name
large
for each
returning,
system
but,
lacks reference to the existence of
I
stars.
can't even say the word.
Milky Way, Magellanic Clouds,
Magellanic,
Andromeda
yeah.
Nebulae. All three were named before telescopes were invented, so they could not yet be resolved into their stellar constituencies. As detailed in Chapter 9, without the benefit of telescopes operating in multiple bands of light, we might still declare the space between the galaxies to be
Chapter
empty.
9, we're at Chapter 4.
Aided by
Jeez,
modern
alright.
detectors and modern theories,
So
we
got
have
a few
probed our
chapters.
cosmic countryside and revealed all manner of hard-to-detect things. Dwarf galaxies, runaway stars that explode, million-degree X-ray emitting gas, dark matter, faint blue galaxies, ubiquitous gas clouds, super-duper high-energy charged particles, and the mysterious quantum vacuum energy. With a list like that, one could argue that all the fun in the universe happens between the galaxies rather than within them. In any reliably surveyed volume of space, dwarf galaxies outnumber large galaxies by more than 10 to 1. The first essay I ever wrote on the universe in the early 1980s was titled The Galaxy and the Seven Dwarfs,
Alright, so
referring
there's
to the
12
Milky Way's
chapters.
diminutive
And we're
nearby
in Chapter
family.
4 right now.
Since then, the tally of local dwarf galaxies has been counted in the dozens. While full-blooded galaxies contain hundreds of billions of stars, dwarf galaxies can have as few as 1 million, which renders them 100,000 times harder to detect. No wonder they're still being discovered in front of our noses. Images of dwarf galaxies that no longer manufacture stars tend to look like tiny, boring smudges. Those dwarfs that do form stars are all irregularly shaped and, quite frankly, are a sorry-looking lot. Dwarf galaxies have 3 things working against their detection. They're small, and so they're easily passed over when seductive spiral galaxies vie for your attention. They're dim, and so are missed in many surveys of galaxies that cut off below a pre-specified brightness level. And they have low density of stars within them, so they offer poor contrast above the glow of surrounding light from Earth's nighttime atmosphere and from other sources. All this is true, but since dwarfs far outnumber normal galaxies, perhaps our definition of what is normal needs revision.
Yes.
You will find most known
thought about
dwarf
that as
galaxies
well.
hanging out near bigger galaxies, in orbit around them like satellites. The 2 Magellanic Clouds are part of the Milky Way's dwarf family. But the lives of satellite galaxies can be quite hazardous. Most computer models of their orbits show a slow decay that ultimately results in the hapless dwarfs getting ripped apart and then eaten by the main galaxy. The Milky Way engaged in at least one
the
act of
normal
cannibalism in the
galaxy.
last billion years, when it consumed a dwarf galaxy whose flayed remains can be seen as a stream of stars orbiting the galactic center beyond the stars of the constellation Sagittarius.
Oh,
The
really?
system
I
is
didn't even
called
know
the
about that.
Sagittarius dwarf, but should probably have been named Lunch.
I've never heard. I never knew that the Milky Way gobbled up another. Well, I mean, it is the Milky Way. It has a whole lot of stars and stuff in it, but I never thought that it could gobble up a dwarf star and leave its remnants out for us to find in Sagittarius. Apparently, that's. Oh my god, that's cool. I wonder how many stars was in the leftover stuff. Probably millions or something stupid like that. Something too hard to comprehend.
In the high-density environment of clusters, 2 or more large galaxies routinely collide and leave behind a titanic mess. Spiral structures warped beyond all recognition. Newly induced bursts of star-forming regions spawn from the violent collisions of gas clouds, and hundreds of millions of stars strewn hither and yon, having freshly escaped the gravity of both galaxies. Some stars reassemble to form blobs that could be called dwarf galaxies. Other stars remain adrift. About 10% of all large galaxies show evidence of a major gravitational encounter with another large galaxy, and that rate may be 5 times higher among galaxies and clusters.
Oh, wow.
With all this mayhem, how much galactic flotsam permeates intergalactic space, especially within clusters? Nobody knows for sure. The measurement is difficult because isolated stars are too dim to detect individually. we must rely on detecting a faint glow produced by the light of all stars combined. In fact, observations of clusters detect just such a glow between the galaxies, suggesting that there may be as many vagabond, homeless stars as there are stars within the galaxies themselves. Adding ammo to the discussion, we have found, without looking for them, more than a dozen supernovas that exploded far away from what we presume to be their host galaxies. In ordinary galaxies, for every star that explodes in this way, 100,000 to 1,000,000 do not. So isolated supernovas may betray entire populations of undetected stars. Supernovas are stars that have blown themselves to smithereens and, in the process, have temporarily, over several weeks, increased their luminosity 1,000,000,000-fold, making them visible across the universe. While a dozen homeless supernovas is a relatively small number, many more may await discovery, since most supernova searches systematically monitor known galaxies and not empty space. There's more to clusters than their constituent galaxies and their wayward stars. Measurements made with X-ray sensitive telescopes reveal a space-filling intracluster gas at tens of millions of degrees. The gas is so hot that it glows strongly in the X-ray part of the spectrum. The very movement of gas-rich galaxies through this medium eventually strips them of their own gas, forcing them to forfeit their capacity to make new stars. That could explain it, but when you calculate the total mass present in this heated gas, for most clusters, it exceeds the mass of all galaxies in the cluster by as much as a factor of 10.
Jesus.
Worse yet, clusters are overrun by dark matter, which happens to contain up to another factor of 10 times the mass of everything else. In other words, if telescopes observed mass rather than light, then our cherished galaxies and clusters would appear as insignificant blips amid a giant spherical blob of gravitational forces. In the rest of space, outside of
this is
clusters,
getting too much.
there's a population of
Can't even
galaxies that
comprehend
thrived long ago.
what he's saying.
As already noted, looking out into the cosmos
Like, I get
is
a bit of it,
analogous
but
to a geologist looking across sedimentary strata, where the history of rock formation is laid out in full view. Cosmic distances are so vast that the travel time for light to reach us can be millions or even billions of years. When the universe was half its current age, a very blue and very faint species of intermediate-sized galaxy thrived. We see them. They hail from a long time ago, representing galaxies far, far away. Their blue comes from the glow of freshly formed, short-lived, high-mass, high-temperature, high-luminosity stars. The galaxies are faint, not only because they are distant, but because the population of luminous stars within them was thin. Like the dinosaurs that came and went, leaving birds as their only modern descendant, the faint blue galaxies no longer exist, but presumably have a counterpart in today's universe. Did all their stars burn out? Have they become invisible corpses strewn throughout the universe? Did they evolve into the familiar dwarf galaxies of today? Or were they all eaten by larger galaxies? We do not know, but their place in the timeline of cosmic history is certain. With all this stuff between the big galaxies, we might expect some of it to obscure our view of what lies beyond. This could be a problem for the most distant objects in the universe, such as quasars. Quasars are superluminous galaxy cores whose light has typically been traveling for billions of years across space before reaching our telescopes. As extremely distant sources of light, they make ideal guinea pigs for the detection of intervening junk. Sure enough, when you separate quasar light into its component colors, revealing a spectrum, it's riddled with the absorbing presence of intervening gas clouds. Every known quasar, no matter where on the sky it's found, shows features from dozens of isolated hydrogen clouds scattered across time and space. This unique class of intergalactic object was first identified in the 1980s and continues to be an active area of astrophysical research. Where do they come from? How much mass do they all contain? Every known quasar reveals these hydrogen features, so we conclude that the hydrogen clouds are everywhere in the universe. And as expected, the farther the quasar, the more clouds are present in the spectrum. Some of the hydrogen clouds, less than 1%, are simply the consequence of our line of sight passing through the gas contained in an ordinary spiral or irregular galaxy. You would, of course, expect at least some quasars to fall behind the light of ordinary galaxies that are too distant to detect. But the rest of the absorbers are unmistakable as a class of cosmic object. Meanwhile, quasar light commonly passes through regions of space that contain monstrous sources of gravity, which wreak havoc on the quasar's image. These are often hard to detect because they may be composed of ordinary matter that is simply too dim and distant, or they may be zones of dark matter, such as what occupies the centers and surrounding regions of galaxy clusters. In either case, where there is mass, there is gravity. And where there's gravity, there is curved space, according to Einstein's general theory of relativity. And where space is curved, it can mimic the curvature of an ordinary glass lens and alter the pathways of light that pass through.
Yeah, so that's how we see planets from further back than what we could actually see. We can go on the edge of a black hole, for example, and the curvature of the planets that are being magnified behind it is what's allowing us to see places that we wouldn't be able to normally see if we just stared at that normal region. But it's because the black hole's acting like a magnifying glass is what's letting us see further than what we can, if that makes sense. Not the black hole itself, but what would you call it? The outside rim of it is what is magnifying whatever's behind it, so we can see it. And I think that's how the oldest galaxy, I think it's the oldest galaxy was found, using a black hole and its magnifying technique, which is it's pretty fucking cool to be able to even do that.
Distant quasars and whole galaxies have been lensed by objects that happen to fall along the line of sight to Earth's telescopes. Depending on the mass of the lens itself and the geometry of the line of sight alignments, the lensing action can magnify, distort, or even split the background source of light into multiple images, just like funhouse mirrors at arcades. One of the most distant known objects in the universe is not a quasar, but an ordinary galaxy.
This is what I was saying.
Feeble light has been magnified significantly by the action of an intervening gravitational lens.
See?
We may henceforth need
crazy
to rely upon these intergalactic telescopes to peer where and when ordinary telescopes cannot reach, and thus reveal the future holders of the cosmic distance record.
And that's I think it was 14
Nobody doesn't like
or
intergalactic space,
13.6
but it
billion
can be
years.
hazardous to your health if you choose to go there.
Galaxy
Let's ignore the fact that you would
found?
freeze to death
Pretty
as
crazy.
your warm body tried to reach equilibrium with the 3-degree temperature of the universe. And let's ignore the fact that your blood cells would burst while you suffocated from the lack of atmospheric pressure.
Yeah,
These
sure.
are ordinary dangers. From the Department of Exotic Happenings, intergalactic space is regularly pierced by super-duper high-energy, fast-moving, charged subatomic particles. We call them cosmic rays. The highest energy particles among them have 100 million times the energy that can be generated in the world's largest particle accelerators. Their origin continues to be a mystery, but most of these charged particles are protons, the nuclei of hydrogen atoms, and are moving at 99.9999999999999% of the speed of light. Remarkably, these single subatomic particles carry enough energy to knock a golf ball from anywhere on a putting green into the cup. Perhaps the most exotic happenings between and among the galaxies in the vacuum of space and time is the seething ocean of virtual particles.
How many nines
Undetectable matter and antimatter pairs popping in and out of existence. This peculiar prediction of quantum physics has been dubbed the vacuum energy, which manifests as an outward pressure acting counter to gravity that thrives in the total absence of matter. The accelerating universe, dark energy incarnate, may be driven by the action of this vacuum energy. Yes, intergalactic space is and will forever be where the action is.
That's crazy.
Chapter 5. dark matter.
I should end it here, but I'm not going to.
Gravity, the most familiar of nature's forces, offers us simultaneously the best and the least understood phenomena in nature. It took the mind of the millennium's most brilliant and influential person, Isaac Newton, to realize that gravity's mysterious action at a distance arises from the natural effects of every bit of matter, and that the attractive force between any two objects can be described by a simple algebraic equation. It took the mind of the last century's most brilliant and influential person, Albert Einstein, to show that we can more accurately describe gravity's action at a distance as a warp in the fabric of space-time, produced by any combination of matter and energy. Einstein demonstrated that Newton's theory requires some modification to describe gravity accurately,
I haven't heard
to
him
predict,
talk
for
about
example,
Stephen
how much
Hawking
light
yet.
rays will bend
Surely
when they
that
pass
happened.
by a massive object. Although Einstein's equations are fancier than Newton's, they nicely accommodate the matter that we have come to know and love, matter that we can see, touch, feel, smell, and occasionally taste. We don't know who's next in the genius sequence, but we've now been waiting nearly a century for somebody to tell us why the bulk of all the gravitational force that we've measured in the universe, about 85% of it, arises from substances that do not otherwise interact with our matter or energy. Or maybe the excess gravity doesn't come from matter and energy at all, but emanates from some other conceptual thing. In any case, we are essentially clueless. We find ourselves no closer to the answer today than we were when this missing mass problem was first fully analyzed in 1937 by the Swiss-American astrophysicist Fritz Zwicky.
1937, jeez, that was a long time ago. But yeah, like, it's probably obvious that we don't know everything. How could we know everything? It's just going to take time until people can work out new maths and other stuff for it. So we're going pretty good for where we are now. What is it? I'd say 500 years or something from going to knowing or talking about one thing to being where we are now. That's pretty good odds. So we're probably going to find it within the next 500 years to 1,000 years, no doubt.
He taught at the California Institute of Technology
Just sucks that
for
we
more
won't
than
be here
40
for it.
years, combining his far-ranging insights into the cosmos with a colorful means of expression and an impressive ability to antagonize his colleagues. Zwicky studied the movement of individual galaxies within a titanic cluster of them, located far beyond the local stars of the Milky Way, that trace out the constellation Coma Berenices, the hair of Berenice, an Egyptian queen of antiquity. The Coma cluster, as we call it, is an isolated and richly populated ensemble of galaxies about 300 million light-years from Earth. Its 1,000 galaxies orbit the cluster's center, moving in all directions like bees swarming a beehive.
Yeah, right.
Using the motions of a few dozen galaxies as tracers of the gravity field that binds the entire cluster, Zwicky discovered that their average velocity had a shockingly high value. Since larger gravitational forces induce higher velocities in the objects they attract, Zwicky inferred an enormous mass for the Coma cluster. As a reality check on that estimate, you can sum up the masses of each member galaxy that you see. And even though Coma ranks among the largest and most massive clusters in the universe, it does not contain enough visible galaxies to account for the observed speeds Zwicky measured. How bad is the situation? Have our known laws of gravity failed us? They certainly work within the solar system. Newton showed that you can
We don't
derive
know
the unique
everything.
speed that a planet must
Simple as
have
that.
to maintain a stable orbit at any
Give it
distance from
time.
the Sun, lest it descend back towards the Sun or ascend to a farther orbit. Turns out, if we could boost Earth's orbital speed to more than the square root of 2, 1.4142 ... times its current value, our planet would achieve escape velocity and leave the solar system entirely. We can apply the same reasoning to much larger systems, such as our own Milky Way galaxy, in which stars move in orbits that respond to the gravity from all the other stars. Or in clusters of galaxies, where each galaxy likewise feels the gravity from all the other galaxies. In this spirit, amid a page of formulas in his notebook, Einstein wrote a rhyme, more ringingly in German than in this English translation, in honor of Isaac Newton. Look unto the stars to teach us how the master's thoughts can reach us. Each one follows Newton's math, silently along its path. When we examine the Coma cluster, as Zwicky did during the 1930s, we find that its member galaxies are all moving more rapidly than the escape velocity for the cluster. The cluster should swiftly fly apart, leaving barely a trace of its beehive existence after just a few 100 million years had passed. But the cluster is more than 10 billion years old, which is nearly as old as the universe itself. And so was born what remains the longest-standing unsolved mystery in astrophysics. Across the decades that followed Zwicky's work, other galaxy clusters revealed the same problem, so Coma could not be blamed for being peculiar. Then what or who should we blame? Newton? I wouldn't, not just yet.
Not yet.
His theories have been examined for 250 years and passed all tests. Einstein? No. The formidable gravity of galaxy clusters is still not high enough to require the full hammer of Einstein's general theory of relativity, just 2 decades old when Zwicky did his research. Perhaps the missing mass needed to bind the Coma cluster's galaxies does exist, but in some unknown invisible form. Today, we've settled on the moniker dark matter, which makes no assertion that anything is missing, yet nonetheless implies that some new kind of matter must exist, waiting to be discovered. Just as astrophysicists had come to accept dark matter in galaxy clusters as a mysterious thing, the problem reared its invisible head once again. In 1976, the late Vera Rubin, an astrophysicist at the Carnegie Institution of Washington, discovered a similar mass anomaly within spiral galaxies themselves. Studying the speeds at which stars orbit their galactic centers, Rubin first found what she expected. Within the visible disk of each galaxy, the stars farther from the center move at greater speeds than the stars close in. The farther stars have more matter, stars and gas, between themselves and the galaxy center, enabling their higher orbital speeds. Beyond the galaxy's luminous disk, however, one can still find some isolated gas clouds and a few bright stars. Using these objects as tracers of the gravity field exterior to the most luminous parts of the galaxy, where no more visible matter adds to the total, Rubin discovered that their orbital speeds, which should now be falling with increasing distance out there in Nowheresville, in fact, remained high. These largely empty volumes of space,
how they remain high being so far away,
of each galaxy, contain too little visible matter to explain the anomalously high orbital speeds of the tracers. Rubin correctly reasoned that some form of dark matter must lie in these far-out regions, well beyond the visible edge of each spiral galaxy. Thanks to Rubin's work, we now call these mysterious zones dark matter halos. This halo problem exists under our noses, right in the Milky Way. From galaxy to galaxy and from cluster to cluster, the discrepancy between the mass tallied from visible objects and the object's mass estimated from total gravity ranges from a factor of a few up to, in some cases, a factor of many hundreds. Across the universe, the discrepancy averages to a factor of 6. Cosmic dark matter has about 6 times the total gravity of all the visible matter. Further research has revealed that the dark matter cannot consist of ordinary matter that happens to be underluminous or non-luminous. This conclusion rests on 2 lines of reasoning. First, we can eliminate with near certainty all plausible familiar candidates, like the suspects in a police lineup. Could the dark matter reside in black holes? No, we think that we would have detected this many black holes from their gravitational effects on nearby stars. Could it be dark clouds? No, they would absorb or otherwise interact with light from stars behind them, which bona fide dark matter doesn't do. Could it be interstellar or intergalactic rogue planets, asteroids, and comets, all of which produce no light of their own? It's hard to believe that the universe would manufacture 6 times as much mass in planets as in stars. That would mean 6,000 Jupiters for every star in the galaxy, or worse yet, 2 million Earths. In our own solar system, for example, everything that is not the sun adds up to less than 1/5 of 1% of the sun's mass. More direct evidence for the strange nature of dark matter comes from the relative amount of hydrogen and helium in the universe. Together, these numbers provide a cosmic fingerprint left behind by the early universe. To a close approximation, nuclear fusion during the first few minutes after the Big Bang left behind 1 helium nucleus for every 10 hydrogen nuclei, which are themselves simply protons.
Yeah.
Calculations show that if most of the dark matter had involved itself in nuclear fusion, there would be much more helium relative to hydrogen in the universe. From this, we conclude.
All right, so let's break that down real quick. He said dark matter was 6 times more dense than normal matter. How is that even possible? And then all these figures that he's going off, I'm just absolutely mind blown by that. I didn't even know. The one that gets me is I didn't even know the dark matter was heavier than normal matter. That is crazy.
Conclude that most of the dark matter, hence most of the mass in the universe, does not participate in nuclear fusion, which disqualifies it as ordinary matter, whose essence lies in its willingness to participate in the atomic and nuclear forces that shape matter as we know it. Detailed observations of the cosmic microwave background, which allow a separate test of this conclusion, verify the result.
Awesome.
Dark matter and nuclear fusion don't mix. Thus, as best as we can figure, the dark matter doesn't simply consist of matter that happens to be dark. Instead, it's something else altogether. Dark matter exerts gravity according to the same rules that ordinary matter follows, but it does little else that might allow us to detect it. Of course, we are hamstrung in this analysis by not knowing what dark matter is in the first place. If all mass has gravity, does all gravity have mass? We don't know. Maybe there's nothing the matter with the matter, and it's the gravity we don't understand.
We don't know.
The discrepancy between dark and ordinary matter varies significantly from one astrophysical environment to another, but it becomes more pronounced for large entities such as galaxies and galaxy clusters. For the smallest objects, such as moons and planets, no discrepancy exists. Earth's surface gravity, for example, can be explained entirely by the stuff that's under our feet. If you're overweight on Earth, don't blame dark matter. Dark matter...
Oh, damn it! That was my go-to, man. I'm a little bit overweight, and I wanted to blame dark matter all my life. Not really. I never even thought of that. Dark matter being 6 times heavier.
Also has no bearing on the moon's orbit around Earth, nor on the movements of the planets around the sun. But as we've already seen, we do need it to explain the motions of the stars around the center of the galaxy. Does a different kind of gravitational physics operate on the galactic scale? Probably not. More likely, dark matter consists of matter whose nature we have yet to divine, and which gathers more diffusely than ordinary matter does. Otherwise, we would detect the gravity of concentrated chunks of dark matter dotting the universe. Dark matter comets, dark matter planets, dark matter galaxies. As far as we can tell, that's not the way things are.
Yeah, but we don't know that for certain yet, because we don't even know what dark matter is. If we work out what dark matter is, like 200, 500, 1,000 years from now, maybe then we could understand if there are such things as dark matter planets or galaxies. Because, like, there's galaxies out there that we see made of matter, right? But, like, there's an awful massive waste of space out there if there's nothing more than that. I'm not saying they're true or not, I just don't cancel it because you don't know or haven't found information yet. We've got years and years, it's always still in the works. So
No, is that the matter we have come to love in the universe, the stuff of stars, planets, and life, is only a light frosting on the cosmic cake, modest buoys afloat in a vast cosmic ocean of something that looks like nothing.
Exactly my point.
During the first 500,000 years after the Big Bang, a mere eye blink in the 14 billion year sweep of cosmic history, matter in the universe had already begun to coalesce into the blobs that would become clusters and superclusters of galaxies. But the cosmos would double in size during its next 500,000 years and continue growing after that. At odds in the universe were two competing effects. Gravity wants to make stuff coagulate, but the expansion wants to dilute it. If you do the math, you rapidly deduce that the gravity from ordinary matter could not win this battle by itself. It needed the help of dark matter, without which we would be living, actually not living, in a universe with no structures, no clusters, no galaxies, no stars, no planets, no people.
So we can think about dark matter as a friend, I guess, because we don't know it as anything else, I guess, and we wouldn't be here without it. So thank you, dark matter. Also, I put up a poll to say if I should do another chapter after this one. So if you guys, because I have to go to bed, but if majority say yes, then I'll keep going.
How much gravity from dark matter did it need? 6 times as much as that provided by ordinary matter itself. Just the amount we measure in the universe. This analysis doesn't tell us what dark matter is, only that dark matter's effects are real, and that, try as you might, you cannot credit ordinary matter for it. So, dark matter is our frenemy.
Yeah,
We have
exactly.
no clue what it is. It's kind of annoying, but we desperately need it in our calculations to arrive at an accurate description of the universe.
It's like that one friend at
Scientists
school.
are generally uncomfortable whenever
You
we
don't
must
really
base our
like, but he's good
calculations
to have
on
around.
concepts we don't understand. But we'll do it if we have to. And dark matter is not our first rodeo. In the 19th century, for example, scientists measured the energy output of our sun and showed its effect on our seasons and climate long before anyone knew that thermonuclear fusion is responsible for that energy. At the time, the best ideas included the retrospectively laughable suggestion that the sun was a burning lump of coal. Also in the 19th century, we observed stars, obtained their spectra, and classified them long before the 20th century introduction of quantum physics, which gives us our understanding of how and why these spectra look the way they do. Unrelenting skeptics might compare the dark matter of today to the hypothetical, now defunct ether proposed in the 19th century as the weightless, transparent medium permeating the vacuum of space through which light moved. Until a famous 1887 experiment in Cleveland showed otherwise, performed by Albert Michelson and Edward Morley at Case Western Reserve University, scientists asserted that the ether must exist, even though not a shred of evidence supported this presumption. As a wave, light was thought to require a medium through which to propagate its energy, much as sound requires air or some other substance to transmit its waves. But light turns out to be quite happy traveling through the vacuum of space, devoid of any medium to carry it. Unlike sound waves, which consist of air vibrations, light waves were found to be self-propagating packets of energy requiring no assistance at all. Dark matter ignorance differs fundamentally from ether ignorance. The ether was a placeholder for our incomplete understanding, whereas the existence of dark matter derives not from mere presumption, but from the observed effects of its gravity on visible matter. We're not inventing dark matter out of thin space. Instead, we deduce its existence from observational facts. Dark matter is just as real as the countless exoplanets discovered in orbit around stars other than the Sun, discovered solely through their gravitational influence on their host stars, and not from direct
It's
measurement
crazy
of their
that we
light.
don't know what it is.
The worst that can happen is we discover that dark matter does not consist of matter at all, but of something else. Could we be seeing the effects of forces from another dimension? Are we feeling the ordinary gravity of ordinary matter crossing the membrane of a phantom universe adjacent to ours? If so, this could be just one of an infinite assortment of universes that comprise the multiverse. Sounds exotic and unbelievable. But is it any more crazy than the first suggestions that Earth orbits the Sun? That the Sun is one of 100 billion stars in the Milky Way? Or that the Milky Way is but one of 100 billion galaxies in the universe? Even if any of these fantastical accounts prove true,
Pretty crazy.
none of it would change the successful invocation of dark matter's gravity in the equations that we use to understand the formation and evolution of the universe.
it's pretty crazy how many stars and galaxies and all that are out there. Really, if you think about it, because like back in old times, I'll say really old times, where they believed that Earth was the center. It was like, yeah, okay, I understand why. And then someone comes along and says, well, no, we orbit this thing called the sun, or this giant plasma ball. And people, like, nearly. They tried to cancel him, this guy, I can't remember his name, and, like, discredit all his work and all that sort of stuff. And now many like people have come to prove that that's true, and everyone here knows it's true. And then for fast forward to now, where we don't know what dark matter is, and people put out the same sort of thing, and they're like, "Oh, it could be this, this, this," and people are discrediting those people, and we just don't know yet. So it's unfortunately none of us will be around to probably know what dark matter actually is, but it's cool to comprehend and think about.
Other unrelenting skeptics might declare that seeing is believing, an approach to life that works well in many endeavors, including mechanical engineering, fishing, and perhaps dating. It's also good, apparently, for residents of Missouri, but it doesn't make for good science. Science is not just about seeing, it's about measuring, preferably with something that's not your own eyes, which are inextricably conjoined with the baggage of your brain. That baggage is more often than not a satchel of preconceived ideas, post-conceived notions, and outright bias.
Well,
Having resisted attempts to detect it directly on Earth for 3/4 of a century, dark matter remains in play. Particle physicists are confident that dark matter consists of a ghostly class of undiscovered particles that interact with matter via
what I'm
gravity,
saying,
but otherwise interact with matter or
it's not
light
like it's
only
some
weakly
fake thing
or
that
not at
people have
all.
made up. It's
If
an
you like
actual
gambling
thing.
on physics, this option is a good bet. The world's largest particle accelerators are trying to manufacture dark matter particles amid the detritus
I
of
hope they
particle
do.
collisions. And specially designed laboratories buried deep underground are trying to detect dark matter particles passively in case they wander in from space. An underground location naturally shields the facility from known cosmic particles that might trip the detectors as dark matter imposters. Although it could all be much ado about nothing, the idea of an elusive dark matter particle has good precedence. Neutrinos, for instance, were predicted and eventually discovered, even though they interact extremely weakly with ordinary matter. The copious flux of neutrinos from the Sun, 2 neutrinos for every helium nucleus fused from hydrogen in the Sun's thermonuclear core,
So I'm curious how
exit
they
the Sun
actually found out
unfazed by the Sun
neutrinos.
itself, travel through the vacuum of space at nearly the speed of light, then pass through Earth as though it does not exist. The tally? Night and day, 100 billion neutrinos from the Sun pass through each thumbnail square patch of your body every second,
Oh,
without
wow.
a trace of interaction with your body's atoms.
Wow.
In spite of this elusivity, neutrinos are nonetheless stoppable under special circumstances, and if you can stop a particle at all, you've detected it. Dark matter particles may reveal themselves through similarly rare interactions, or, more
That's
amazingly,
crazy.
they might manifest via forces other than the strong nuclear force, weak nuclear force, and electromagnetism. These 3 plus gravity complete the Fab 4 forces of the universe, mediating all interactions between and among all known particles. So the choices are clear. Either dark matter particles must wait for us to discover and control a new force or class of forces through which their particles interact, or else dark matter particles interact via normal forces, but with staggering weakness. So, dark matter's effects are real. We just don't know what it is. Dark matter seems not to interact through the strong nuclear force, so it cannot make nuclei. It hasn't been found to interact through the weak nuclear force, something even elusive neutrinos do.
Must be strange.
It
or
doesn't seem
charmed.
to interact with the electromagnetic force, so it doesn't make molecules and concentrate
No,
into
I'm not
dense
talking
balls of dark
forces,
matter.
I'm talking quarks.
Nor does it absorb or emit or reflect or scatter light. As we've known from the beginning, dark matter does indeed exert gravity, to which ordinary matter responds. But that's it. After all these years, we haven't discovered it doing anything else.
So there's got to be something we're missing in those four things, right? Surely. If it only detects gravity and it doesn't have strong or weak magnetic force or the electromagnetic, I believe it was, then clearly there's something there that we're missing.
For now, we must remain content to carry dark matter along as a strange, invisible friend, invoking it where and when the universe requires it of us.
Yes, sir.
Chapter 6.
Alright, new chapter. Should I continue or not? I don't know. It's up to you guys. I'm going to have a quick toilet break. In the meantime, vote on my poll that I put up to say if I should continue this one or not for another chapter. And if I don't see any response, then that will probably be the end of my stream until part 2. Because it's like 6:30 now, and I have to be up at work at 1:30 in the morning. So, but I'm prepared to keep going. It's up to you guys. Bear in mind there's 12 chapters in this book, and we're at 6. So there definitely will be a part 2. We've got like 2 hours left of this audiobook, so whether it gets split into 3 or not is another thing. But I'll give you a minute to decide if we should continue or not, or just end it here and do a part 2. So it's up to you guys. I can do one more chapter, and depending on... So we're at 1 hour 27 now, and it goes for 3 hours 41. So it's up to you guys. Man, this is crazy. This book is actually insane. I think I might buy it. Because I do better understanding when I read the words, not so much listen to it. Although listening to it is really good as well. Yeah. And like, I don't know, man. I like it. Science is good. What else can I say? Alrighty, so my poll's been up for 22 minutes, and none of you have said yes or no to continuing to a chapter, so I think this will be the end. I guess. Yeah, I'll wait. I want to listen to more, but I'll wait until you guys actually want to hang around and listen to it as well. So, yeah, it was good fun. It's a good talk. We'll continue this on. Again, I am just putting in here in the chat the context so I know where to continue on from, which is that. And I will check that next time I start. But be sure that you guys like it and subscribe to keep in touch of when I'm doing my next one. I don't know when I'll do the part 2, but I want to do it soon, obviously, because I love this stuff. But I have to go to bed, get up early and all that sort of fun stuff. So, yeah, I hope you guys enjoyed, and we will do another one soon. So thanks for watching, and that's it. See you next time.